Hi everyone. Here is your lesson for Chapter 7, Lesson 2. It is on experimental and theoretical probability. Your learning target is to be able to develop probability models using experimental and theoretical probability. And you'll know if you've done that if you can explain the meanings of experimental probability and theoretical probability. You can find experimental and theoretical probabilities, and you can use probability to make predictions. Please pause at this moment and write down your first vocabulary word. Your first key idea is experimental probability. That is probability that's based on repeated trials of an experiment. The probability of an event is the number of times the event occurs divided by the total number of trials. So for example, if you flipped a coin 10 times and you landed 4 heads, your experimental probability would be 0.4. Example 1, finding an experimental probability. The table shows results of spinning a penny 25 times. What is the experimental probability of spinning heads? So this is very similar to the one I just shared with you about flipping a coin, but this time you're going to spin it. So it lands heads 6 times, tails 19 times. So 19 plus 6 is a total of 25 times that it's spun. We want to find what is the experimental probability of spinning heads. So that would be 6 over 25, and then 6 divided by 25 equals 0.24. And if you wrote it as a percent, that would be 24%. We could also say that that is unlikely. Now it's your turn. Please try it. The table shows the results of rolling a number cube 50 times. Find the experimental probability of each event. Then push play when you're ready for the answers. Taking a look at the table, you can see across the top the numbers rolled. And this is a 6-sided number cube, so it makes sense that we have the numbers 1 through 6. The frequencies must be added to get a total number of rolls. 10 plus 4 is 14, plus 8 is 22, plus 11 is 44, and plus 6 is 50. So then we look at rolling a 3. A 3 was rolled 8 times. So we would go 8 out of 50. We'd say that's 0.16, 16%, or you could say it's unlikely. But when you get to a situation where you are rolling a number cube with 6 possible outcomes, all of the events technically would be considered unlikely, just because there's so many different possible outcomes. So now we look at rolling an odd number. So we have 1, 3, and 5. So we'd add up 10 plus 8 is 18. 18 plus 11 more, that would be 29. And there's still 50 possible outcomes. So 29 divided by 50 gives you a probability of 0.58, 58%, and we would actually now say that one is likely. Please pause the video here and write down your next vocabulary word or key idea, which is theoretical probability. Theoretical probability is when all possible outcomes are equally likely. The theoretical probability of an event is the quotient, which means a division problem, the quotient of a number of favorable outcomes and the number of possible outcomes. Theoretical probability is a little bit different though than experimental probability, because theoretical is like in theory. You don't actually do the experiment. So in this example, it would be like if you flipped a coin 10 times, how many times should it land heads? And because it's heads or tails, it should land heads half of the time, so 5 out of 10. But the main difference then is theoretical probability is what should happen. Experimental probability will vary a little bit. That's what actually does happen. So for example 2, let's find a theoretical probability. You randomly choose one of the letters shown. So what is the theoretical probability of choosing a vowel? So in this example, we have number of favorable outcomes, which would be choosing a vowel. Vowels are A, E, I, O, U. So we have E, E, and O. So that would be 3. Number of possible outcomes, there are 7. So 3 divided by 7 is 0.43, 43%, unlikely. For this, try it. What is the theoretical probability of randomly choosing an X? What is the theoretical probability of randomly choosing a consonant? And what is the theoretical probability of not choosing the letter L? Please try these, and then when you're ready, push play for your answers. So theoretical probability of choosing an X. We only have one X, and so we would say that that is desirable outcomes of 1, total possible outcomes of 7. So 1 divided by 7 is going to be 0.14, 14%, unlikely. What's the theoretical probability of randomly choosing a consonant? So there we'd have X, P, L, and R. So that would be 4 out of 7. And so 4 divided by 7 is 0.57, 57%. And we'd say that's likely. And finally, what's the theoretical probability of not choosing an L? Well, there is only one L, so that means 6 out of the 7 would be favorable outcomes for that. 6 divided by 7 is 0.85, 85%, and likely. And some of you may even say that that's very likely. For example 3, we're now comparing probabilities. The bar graph shows the results of rolling a number cube 300 times. How does the experimental probability of rolling an odd number compare with the theoretical probability? So thinking back, experimental probability, that's what actually happens. And here you can see a table showing us what actually happens. So let's look for odd numbers, 1, 3, and 5. So we'll add those together, 48, 50, and 49. And so when we add 48 plus 50 plus 49, we get 147. So 147, that becomes the number of times an odd number was rolled for experimental. So we have 147 over a total of 300. 147 divided by 300 is 0.49, or 49%. Now theoretical, that's the number of times each should be rolled. Well, if we have 6 dice, or 6 sides on a die, 300 divided equally into 6 should be 50, right? So 50 for 1, 50 for 3, and 50 for 5. Theoretically, we should have 150 times where an odd number is rolled, divided by a total of 300. That's going to be 0.5, or 50%. So how does the experimental probability of rolling an odd number compare with the theoretical? The experimental probability ended up being just 1% less. So now this one is for you to try. Please make sure you get this in your notes. How does the experimental probability of rolling a number greater than 1 compare with the theoretical probability? And we're using the same data from rolling a number cube as we did for our example number 3. So you go ahead and try it. Hit play when you're ready. All right, so number greater than 1. So that means it can't be 1. So let's start out with experimental. Experimental probability. We have 53, 50, 52, 49, and 48. So let's add all those together. 53 plus 50 plus 52 plus 49 plus 48. And we get 252. That's how many possible ways there are to not get a 1. Or, in other words, to get a number greater than 1. And there were 300 times that the number cube was rolled. So 252 divided by 300 is 0.84, or 84%. Very likely. Now for the theoretical. Theoretically, each one of these should be 50, because 300 divided by 6, because it's a 6-sided cube, would be 50. And we had 5 numbers that would be greater than 1. So 5 times 50 would be 250 divided by 300. So 250 divided by 300 comes out to be 0.83, or 83%. So we would say in this situation, the experimental probability was 1% higher. Now for our final example, we're going to use experimental probability. A bag contains 50 marbles, and you randomly draw a marble from the bag, you record its color, and then you put it back in the bag. The table shows the results after 30 draws. Predict the number of red marbles in the bag. So let's find the experimental probability of drawing a red marble. So, the number of times the event occurs. A red marble looks like it has been chosen 9 times. Altogether, we have 3 and 12 is 15. 15 and 9 is 24, and 6 more is 30. So we'll take 9/30. That is 0.3. And that's 30%. To make a prediction, multiply the probability of drawing red, which is 0.3, times the total number of marbles in the bag. So we know back in the original problem, it says a bag contains 50 marbles. 0.3 is the probability of drawing red. 50 is how many marbles are in the bag. So when we multiply those together, we get 15. So we would say you can predict that there are 15 red marbles in the bag. Now here's one for you to try. An inspector randomly selects 200 pairs of jeans and finds 5 defective pairs. About how many pairs of jeans do you expect to be defective in a shipment of 5,000? So what we'll do here is we'll find that there were 5 defective pairs out of a total of 200. So 5 divided by 200 is going to give us the probability of a pair of genes being defective, which is 0.025 or 2.5% of the genes. So our probability here, we'll take 0.025, multiply that by 5,000, and we'll find that there are approximately 125 pairs out of the 5,000 that will also end up being defective. So for example 5, we're looking at modeling in real life. And the question says the theoretical probability of winning a bobblehead when spinning a prize wheel is 1 out of 6. The wheel has 18 selections. So how many selections have a bobblehead as a prize? So we would use our same formula, our probability P is going to equal the number of selections that are considered a win divided by the total number of selections. So let's go ahead and do some substitution then. And what we'll substitute is we know the theoretical probability of winning a bobblehead is 1/6. So we'll put that in right there for the probability. The number of selections, we don't know, because our question says how many selections have a bobblehead as a prize. So no idea. And we'll divide that by the total selections, which the question states is 18. And so now we can do cross product. 1 times 18 is 18. 18 equals 6x. Divide both sides both by 6. And we get x equals 3. So 3 of the selections out of 18 have a bobblehead win as a prize. So for B, the prize wheel is spun 540 times. About how many bobbleheads do you expect to be won? So here's what we can do there. 1 out of 6 are going to win this thing. So we'll take 1 over 6 times 540. 1 divided by 6 is 1.6 repeating times 540. That comes out to be 90. So we would estimate that 90 bobbleheads would be won if the wheel was spun 540 times. And our final slide of the lesson is a try it for you, so please pause the video here. Contestants randomly draw a ticket from a hat and then replace it. The table shows the results after 40 draws. There are 7 winning tickets in the hat. Predict the total number of tickets in the hat. So to set this up, we're going to start with the frequency of a win, which is 2. So our frequency of win is 2. The table shows the results after 40 draws. So 2 out of 40 will result in a win. It then says there are 7 winning tickets in the hat. So the question is, predict how many total tickets are in the hat, which we don't know. So now we can do our cross product here. 7 times 40 is 280 equals 2t. Divide both sides by 2, canceling the 2's on the right side. So we have tickets equals 140. That wraps up your Chapter 7, Lesson 2. Please make sure that if you have any questions, you reach out to your teacher or ask your family at home. Otherwise, I hope you have a good day. Good luck with your practice.